Hey, this is Bradley Bush with another algebra video. Today we're talking about matrix basics for algebra. Our first item in our to-do list is, well, what is a matrix? That's kind of good to know, right? Next, we'll talk about how you can use matrices, and then we'll discuss the two main methods for solving systems of equations using matrices, and those are Gaussian elimination with back substitution and Gauss-Jordan elimination. So, what is a matrix? Well, a matrix is a rectangular structured collection of numbers. So kind of like this thing right here on the right. It's rectangular. It can be square. Oftentimes it helps you with your computations if it's square, but it doesn't have to be square. It could be rectangular, meaning it could have more rows than columns or more columns than rows. But it does have a dimension. And the dimension of the matrix is the number of rows by number of columns. So for example, if you have a 3 by 4, that little X in the middle just means by. So you have a 3 by 4 matrix. That means you have 3 rows and 4 columns. So matrix is the singular version of the word, and matrices is the plural version of the word. All of these, all the matrices are generally named with a capital letter. So here we will call this A. Our matrix capital A has a bunch of elements inside, and those little elements are lowercase a's, and they have a row and a column indicator on them. So A11, that is the first row, first column. A12, that's the element in the first row, second column. A13, that's the element in the first row, third column, and so on. So there are 3 rows in this column, and there are, in this matrix, and there are 3 columns in this matrix. So this is a square matrix. If the row and the column number is identical, meaning a 3 by 3, then they call that a square matrix. There also is something called the main diagonal. The main diagonal is all of the items that are here on this diagonal. They call it the main diagonal because they talk about upper diagonal and lower diagonal, and they use diagonal a lot. But if your row and column indicator is identical, meaning 1, 1, 2, 2, 3, 3, then that element is on the main diagonal. How do we use matrices? Well, we often use matrices to speed up or simplify many problem-solving techniques, especially when we're using computers. It's a really quick way to do computation because you can just drop the variables. Notice down here, you can see I have a matrix here. I don't have any variables in there. So dropping the variables saves us a lot of time. And when we have systems of equations, say in 3 variables like we have here, I have an equation 1, equation 2, equation 3. We can solve this system. It's much faster to do it if we do it with do it in a matrix. So what we will do is we will create a matrix with just the numbers. So it's as if we dropped all of the variables. And notice there's a 2 in front of the x in equation 1. There's a 2 in the first row, first column spot. In the next, if we move down a row, in row 2, column 1, there's a coefficient of 1. And in row 3, there's a coefficient of 1 as well. And you see the coefficients below. So the numbers, positive 1, negative 1, 2, positive 1, negative 1, 2, and 2, 2, negative 1, 2, 2, negative 1. So you can see they all match up. 18, 9, 6, 18, 9, 6. They all match up. We just have dropped the variables. So this is we have a system of equations form. We can represent a system of equations using variables and linear equations. We can also represent the same system in matrix form. There are 2 more vocabulary words that we need to know. First is the coefficient matrix. That is the part of the matrix that comes directly from the left-hand side of the equation, these systems of the equations. So they come from the left-hand side of the equal sign. The augmented matrix, which is the coefficient matrix plus, it includes the right-hand side column as well. So the coefficient matrix and the augmented matrix, those are the two main forms of the matrix that we use for the system of equations. So how do we solve systems of equations with matrices, specifically linear systems of equations with matrices? Well, there are two main methods. One of them is called Gaussian elimination with back substitution, and the other one is Gauss-Jordan elimination. Gauss-Jordan elimination is related to Gaussian elimination, but it just takes a different approach at the end. So let's start with Gaussian elimination with back substitution. We start with our augmented matrix, and then we use something called a row operation. There are three different row operations. They're mathematical operations that you can do that don't change the answer of the system. So it's kind of like algebraically manipulating them, but we're not changing the answer. So we use row operations to change the matrix into a different form, rref, which stands for row echelon form. And the idea behind it, quickly, is we change the first element into a 1, and then we zero out all the bottom elements below that. Then we go over a column, we change the diagonal element into a 1, and then we zero out everything below. And then we keep doing this process, going right a column and down a column until we get to the very bottom. We change that to a 1. And when that's done, then you can see that we have our diagonal elements are all 1s, and everything that's below the diagonal is a 0. Once we've hit that form, that's called row echelon form, and we back substitute. That's when we stop doing our row operations and we just simply back substitute, which means we say, well, this equation really was an equation that had z's in it, it had y's in it, and it had x's in it, right? So this originally is our x column. This is, whoops, that's the wrong color. This is our y column, and our z column is this column. So you can assume that all of those numbers have z's and y's and x's associated with them. So you just change back to equation form, and you're like, hey, I already know what z is because it's solved for, I have zeros all along here, and then I've got a 1. So z equals 3, we know that. We can plug it into the equation above, and then all of a sudden we can solve for y because that's the only variable left. And then when we know y and z, we can plug them back into the top equation and solve for x. So that's a quick version of back substitution. By the way, I have videos that go in more depth in all of these in my algebra playlist, if you want to check those out. So Gauss-Jordan elimination, it starts with the same process as Gaussian elimination does. It just goes a little bit further. So instead of stopping at rref, which we have here, it uses the row operations to go all the way to rref, which is reduced row echelon form. So not only do we have zeros along the main diagonal, and we have, ones along the main diagonal and zeros in the lower diagonal, in the upper diagonal we also have zeros. So we use the same process to zero out the upper diagonal elements. And when we do that, then we literally just read off the answer, because if you remember, again, this has a z by it, and this term, the 1, has a y by it, and this term, I mean, not in the matrix form, but in the system form, right? In the system of linear equations form. And then this has an x by it. So we literally read it off. X equals 5, y equals 2, and z equals 3. So that's super simple. This is your crash course on matrices and solving systems of equations with matrices. If you like it, give me a thumbs up, subscribe to the channel, and thanks for watching.